Okay, good afternoon. Today, we will be discussing complex numbers using Python programming. Okay, I will be discussing here, how to solve complex numbers using Python. So at the end of the lecture, the students will be able to solve complex numbers using CMath module in Python and solve complex numbers, the applications of complex numbers using Python. So I will be giving problem solving, and you are going to solve that using Python. Now, let's start with the very basics of complex number. Okay, recall that your complex number is denoted as A plus JB, where A is the real part of your complex number and where B is the imaginary part of your complex number. Now, to demonstrate that in Python, let's say Z is equals to 3 plus J4, or let's say 4J. Let's make this one a little bit bigger, and this is our Z. Now, if I want to uh, take the real part of Z, we can say, let's print this one. We can say the real part of Z, okay, the real part of Z is just Z dot real. Take note, Z here is the variable. Now, if I will use Z dot real, it will print the real part of your complex number Z. Let's try, run this code. So this is the real part, which is 3.0. So take note, now Z dot real is a floating number. That is a floating number. So you can do that by just typing type Z dot real. So it will give you a float, okay, because that is a floating number. If you will take the type of your Z equals to 3 plus J4, it will give you the type of the variable. So in this case, the variable is actually a complex number. Okay, that's how you use the type. Okay, now let's say if we want to print the imaginary part, we can say the imaginary part of Z, okay, is just Z dot emag. So Z dot emag is the imaginary part of Z. So let's try. Let's print this one. So here we go. The real part of Z is 3.0 and the imaginary part of Z is 4.0. That's how you use Python. That's how you solve the real and the imaginary part of the complex number by just using Python programming. Okay, let's have this one. So supposing we will be discussing math and C modules here. Now, supposing that Z is equals to A plus JB, let's demonstrate it in this manner. Let's say Z is equals to 1 minus 2J. This is my complex number, Z. Z will be equal to 1 minus 2J in this time. Now, let's say I want to convert this rectangular form into polar form. What are we going to do? Take note, now we will be using here CMath module. CMath module is actually the complex mathematics modules for this topic. So we also have here math, but we will be using CMath module. So we are going to import first the module, CMath module, and then we are going to convert this into polar form. Let's say I will create a variable here. Let's say my variable is polar of Z, okay? Let's say polar of Z is just equal to, let's call on CMath because we will be converting this to the equivalent polar coordinate. So CMath, call on CMath dot polar, and then inside the argument is equal to Z. Okay, the argument of your polar should be Z. The argument is actually the function inside. Okay. Let's try. Okay, let's print polar of Z. Okay, polar of Z. So 1 minus 2J in polar form, this is equivalent to 2.23, comma, since this is a polar coordinate, and then we have minus 1.10. 1.10 is actually in radian form. So take note, the angle here is actually represented in radian. So this is the magnitude and this is the angle. So magnitude is also called your modulus, and angle here is also represented by the argument of your complex number. Okay, the argument and the modulus. Now, let's go back to the modulus. When we say modulus of z, say modulus of z. Now let's create another variable named modulus of z. So the modulus of z can be solved using the absolute value of your z. Let's change this one. So let's use the complex numbers that we are all familiar with. So in this case, I will be using 3 minus j4. Okay, and we are going to print. Okay, we are going to print the magnitude. Let's say the magnitude of z is mod z. Take note, mod z is the absolute of z. When we say absolute, that is called the magnitude of z, or we also call this your modulus of z. Let's try. Let's print this one. So you will notice that in the first output, this is the output when we print the polar of z. Actually, this is a coordinate. Okay, this is the coordinate separated by comma. Now, the magnitude of z here is 5.0. Take note of this. This is 5.0. That refers to this magnitude. So magnitude of z is also called the modulus of z. Let's try to find the argument of z. Take note, the argument of z is just the angle of z. Okay, so that is represented by cmat dot face. So cmat dot face of your complex number z. Okay, and then we are going to print. Okay, we will be printing the argument of z. The argument of z is rz. This is in our variable. Let's make this one smaller. Okay, let's print. Okay, now you can see here now the argument and your magnitude, or what we call your modulus of z. Take note. Okay, to separate the magnitude and the argument, you can use abs. That's for the absolute value, and cmat that face, that's for the angle, and the angle is in radian form. Now if you will be using degree angle, so you need to convert that first in radian format. All right, now let's try to convert the polar form into the rectangular form. Okay, let's try this one. Let's convert the polar to rectangular. Let's say rectangular of z is equals to cmat. Take note, this is cmat dot rect. Okay, that's to convert. No, this is how you can see here now, convert polar coordinates to rectangular coordinates. So let's try. Now, what will be the argument here? The argument is very simple. Okay, we need the modulus of z, okay, and the argument of z. So we have this value a while ago. Modulus of z is equals to 5, and the argument of z is equals to negative 0.927295. Okay, now if we are going to print this out, let's say print, okay, the polar equivalent of okay, is, okay, let's call this one is, and then put the variable here, rect of z. That's right. It will convert, okay, the original, okay, polar form to its equivalent rectangular form. Now you can see here, okay, this is 3, okay, minus 3.999J. This is actually approximates now your complex number Z. Okay, that's it for the basic of your CMAT modules. Now, in CMAT modules, we also have CMAT constants. Okay, that is equivalent to pi. Okay, CMAT E is equivalent to Euler's number. CMAT tau is equivalent to twice of your pi. Let's try. Let's say print. Let's print this out. What is the equivalent of CMAT pi? So print CMAT, okay, dot pi. And then we are going to print also, okay, CMAT dot E, okay, and then we will print CMAT dot tau. Okay, I'll run this code. There you go. So 3.14 is actually your value of pi. Of the Euler's number is 2.718, and then tau is 6.28. This is actually twice of your pi. So if you multiply this by 2, the result will be your tau. So that's it for your some of the math constants that we will be using now along the topic. All right, now we go to CMAT powers, square root, and log functions of Z. Okay, now we have this one. We have CMAT that square root. This is equivalent to the square root of Z. We also have CMAT that exp Z, meaning this is e raised to the power of Z. We also have CMAT that log Z now is equivalent to ln of Z. Take note, log of Z is ln, log 10 of Z is your Briggshan logarithm. Log, common logarithm, or what we call Briggshan logarithm. All right, okay, now let's try. Let's demonstrate this one. Let's say I have here a complex number, but before that, we are going to import, okay, CMAT. Now, don't forget this one. Let's say I have here the complex number, Z. Let's say Z is equal to 3 minus 4J. Now, let's use this one. And I have here W equals to 1, 2 plus 5J. So we have two complex numbers, okay? Now let's take the square root. Let's multiply it first, okay? The product, let's say print, no? Let's say print, okay? The product is, okay? We just multiply X and, not X, Z and W. Just multiply and then you can have the product. Let's try it. What's the product? So Z, that is invalid. Take note, why is it invalid? Okay, because this is a complex number. So this is an invalid expression of the product. So how are we going to do this? So we can solve this by using this one. Let's say Y is actually the product. Okay, Z times, let's say 3 minus 4J times 2 plus 5J. And then we are going to print Y. Let's try. Okay, it's still error because it will not print the product. So the product is, so we can say the product is, now we can say, we can print the product first, and then the product is, then print Z times X. That will be valid. Okay. Oh, no, what is this? X is not defined. Okay, by the way, X is not defined here. This is W, Z and W. Okay, that's it. Now the product is equal to 26 plus 7J. You cannot directly print the product now in your print function. So it should be now outside the print function. That's how you print the product. Let's say Let's try the quotient. The quotient. uh, the quotient is, let's try this one. Then we are going to print the quotient. Let's say z divided by w. Let's try. What will happen if we will do this? Okay, this is the quotient. Okay, so the quotient and the product. Okay, that's how you do it in mathematics. Of course, now your reciprocal is 1 over z or 1 over w. That's the reciprocal of your complex number. Okay, now let's try to add some more. Let's say I want to get the square root of z. Okay, the square. We will be utilizing the same code. Now let's just continue it here. So let's say I want to print the square root. Okay, I want to print the square root of z. So how are we going to do that? So let's call on cmath. Okay, that's square root. Then put on the complex number. Let's say I want to print the square root of z. And that's it. Just click print, and here you go. This is now the square root of your complex number z. That's 2 minus j. It's the square root of z. Let's try. Now let's say I am going to print, okay, z raised to w. So this is complex numbers raised to another complex number. Okay. I think we need to put another print here. Let's say the square root of z is, okay, and then let's say print, okay, the, okay, this is a complex numbers. This is complex numbers. Complex number is raised to a complex number. Okay, let's try. So this is the complex numbers raised to complex numbers. Now this will be the result. This is the square root of your z. That's it. No, let's try the exponential function. Let's say we want to print the exponential function of w. Let's say the exponential function of w. So we can say a cmath. Let's call on cmath.exp. That's the exponential function, and then plug in w. So in this case, now we are going to find now the exponential function of w. So let's run the code. So this is the exponential function of w. Okay, it's not that hard. Okay, let's try the logarithm. Let's say what is log of, okay, let's say what is log or ln of negative 5. Okay, question mark. So how are we going to do that? So simple. So we can say cmath dot log. So cmath dot log is actually your ln, and plug in negative 5. So it will print the logarithm of negative 5. Okay, this is the logarithm of your negative 5. Okay, this is positive j. So you have this in your quiz number 1. Okay. Okay, that's it for the logarithm of your complex numbers. Now we go to the trigonometric functions and the hyperbolic functions of z. Let's recall some important things here. Let's say the sine function. Let's put it here. Okay, print. Or let's say import cmath. Okay, actually you can do this once only. But now let's take each problem a new problem. in this case. So let's import CMAT. In this case, now I will be using Z equals to, let's say, 15 minus 8J. This will be the value of my complex number. And I want to take out the trigonometric functions and the hyperbolic functions of your Z. Let's say I want to take let's print this one, the sine of Z. So the sine of Z is simply, you can use CMAT dot sine. Okay, that's how you put CMAT dot sine and put here Z. Print CMAT sine of Z because we are taking the sine of the complex number Z. Easy? Yes, very easy if you are using complex numbers. Let's print line. Okay, I don't know if this will be supported. No, it's not. So let's just print cosine of, let's say, cosine of Z. Cosine of Z is simply print, okay, CMAT dot cosine of Z. Okay, we have the sine of Z and we have the cosine of the complex number Z. Okay, take note. Now, if you are using your calculator, you need to convert. No, you need to use the radian mode in your calculator. Okay, let's try another one. Let's say I want to print the tangent. Okay, the tangent of Z. So the tangent of Z is really simple. Okay, this is just CMAT dot tan of your complex number Z. Okay, that's for the tangent of Z. Let's try some more. Now this time, we will be using the reciprocal function. Let's say I want to print the cosecant of Z. So the cosecant of Z is just equivalent to 1 over secant of Z. So you can say, okay, remove this one. 1 all over CMAT dot secant, CMAT dot cosine of your Z. So this is 1 over CMAT dot cosine of yours is actually the cosecant of Z. This is your cosecant of Z. Same, no? If you are going to, if you are dealing with cotangent or by the way, cosecant is sec. Cosecant is sine, 1 over sine. Okay. Cosecant is 1 over sine, but secant is 1 over cosine. Let's try. Okay, let's add here secant. Okay, secant of Z. Secant of Z is 1 over. Okay, let me correct this one. Okay, what's next? Secant of Z, so that is 1 over CMAT dot cosine. Okay. So for cosecant of Z, that is 1 over sine. For secant, that is 1 over cosine. Of course, for tangent, for cotangent, that is 1 over tangent. Okay, that's it for the trigonometric functions. Let's try to have the hyperbolic function. Let's say I want to print the hyperbolic, okay, hyperbolic cosine of Z. Now, this is cosine, right? So this is hyperbolic cosine of Z. So what are we going to do next? Colon CMAT dot cosine hyperbolic of Z. Then press run. And what is invalid? Okay, invalid because we don't have a delimiter here. So we need to enclose this with a single quotation. All right. Run the code. That's it. That is the hyperbolic cosine of your complex number. Let's say I want to take the hyperbolic cosecant. Okay, hyperbolic cosecant. Let's say print hyperbolic cosecant of z. Take note, cosecant is 1 over sine. So let's say print, okay, CMAT, okay, let's say 1 over CMAT, okay, then sine hyperbolic of z. That is really simple. Take note, hyperbolic cosecant is 1 over CMAT dot sine hyperbolic of z. Run the code. There you go. You have your hyperbolic cosecant of z. So that is really easy, especially when you are using your complex numbers using Python. Now, let's go to the inverse trigonometric and hyperbolic function. So for the inverse trigonometric, let's have this value. First, now we are going to import the module CMAT, and we have this value 0.2 minus 0.4 j. So this will be our value of z. This time we are going to print the inverse. Okay, inverse, or shall we say the arc sine. Okay, the arc sine of z. That's right. Now let's print the arc sine of z. So for the arc sine of z, now this is very simple. Just call on CMAT. Okay, this is CMAT. That arc sine is a sine. Take note, arc sine is a sine. A sine h is the hyperbolic of, okay, the inverse hyperbolic sine of z. So your argument z, and then run the code. That is the arc sine of z. Now, if you will notice, I did not give this lesson now before your quiz, no, because your quiz will look easy now when you know how to use Python. And besides, now when I'm doing your quiz question, I use Python to check my answers if it is right or wrong. Okay, now let's try to do another one. Let's print the arc tangent. Let's say arc tangent of z. So the arc tangent of z is very simple. Okay, just type CMAT dot arc tangent, a tan of z. Okay, run the code, and there you go. You have the arc tangent of z. Now let's have the inverse hyperbolic function, or shall we say another one. Let's say arc. Let's say print the arc. Okay. Okay, arc secant. Okay, let's say arc secant of z. So what is the arc secant of z? So let's correct this out. And then we are going to print the arc secant of z. Take note, secant is just 1 over cosine. Since this is arc secant of z, we need to manipulate z. So take note. Take note. I will be putting my comment here. So take note. So this is a comment. Okay. If I will let a equals to arc secant, okay, arc secant of z, then what will happen here? Then if I'm going to transfer arc secant to the other side of the equation, it becomes secant. So secant of a is now equal to z. Take note, secant of a is now equal to z. Okay. Now, if we are going to solve for a, what are we going to do next? Very good. We need to what? We need to reciprocal. Then, if we are going to reciprocate, both sides of the equation, this will become cosine of a. Okay. this will become cosine of A, which is equals to 1 over Z. Now, if we are going to, if, therefore, let's say therefore, okay, therefore, now if we are going to uh, transpose cosine now to the other side of the equation, now what will remain here is A, and that will become the arc, okay, the arc cosine of 1 over Z. So take note of that. So meaning to say, now the arc secant of Z is simply, okay, is simply the arc cosine, okay, arc cosine now of 1 over Z. Take note of that. This is just the arc cosine of 1 over Z. Okay, this is 1 over Z. Let's run the code. There you go. That is the arc secant of Z. The same now if you are dealing with the hyperbolic function. Let's say I want to print, okay, the arc, okay, the arc hyperbolic of, let's say, cosecant of Z. All right, arc hyperbolic cosecant of Z. Okay, now take note. Now, if we are going to reciprocate, no, just like what we did no, a while ago, if we are going to take the reciprocal of Z, it will become 1 over Z. And if you are going to take the reciprocal of cosecant, it will become it will become sine. So since this is hyperbolic, it will become hyperbolic sine. Okay. So now we can have here CMAT that arc hyperbolic sine, okay, hyperbolic sine of H. But this time this is 1 over Z. That's the reciprocal of your complex number. Let's run. Okay, that's it. Now this is actually the arc hyperbolic cosecant of Z. So to make it simple, just reciprocate your Z to become 1 over Z and just use sine or cosine instead of arc cosecant and arc secant. All right, now that's it for um, the inverse trigonometric and hyperbolic functions. I suggest you try this in your previous exam. Okay. Now we go to the applications of complex numbers. Now, this is the application of your complex number. Okay, let me read the problem first. A series simple circuit have the following values. So this should be a simple series circuit. Okay, let's revise the, where is it? It's hidden. Oh no. Okay, that's it, no? Hidden. Okay, application. One cell hidden. Okay. Okay, double click. This is a simple Control X series circuit. Control V. A simple series circuit. Okay. A simple series circuit have the following values. The input voltage is 22, angle of 76 degree volts, and the current and the impedance is okay, this should be a typo, and the impedance, where's this, and the impedance is 8 minus J24. Okay, 8 minus J24. So we are going to calculate the magnitude of the flowing current in the circuit. So take note, using Ohm's law. Now this is very simple using Ohm's law, but we need to calculate the magnitude of the current flowing in the circuit. So take note, we have here the magnitude of the input voltage, and we have here the impedance in complex number form. So let's start the problem by importing. Okay, let's make it larger. CMAT. Take note, now we are going to treat now each problem a new problem. Okay, that is why I I always call on the import CMAT function. Okay, now we go to V. In this case, V is equals to Okay, let's call this one your modulus of V, because that is given, which is equal to 22. Modulus of V is the magnitude of your input voltage. Okay, take note of that. And then we need to find now the magnitude of your complex number. So let's label that as Z, because this is the impedance. So let's label that as Z. So your impedance is, what is the, okay, 8. Now 8 is the real part minus J24. This is 8 minus J24. 24J. 8 minus 24J. Now, we've learned a while ago to solve the magnitude, no, or the modulus of your complex number. That is using the abs function. So we can say abs Z. Okay. Now, to solve for the magnitude of the current flowing, we can say I is equal to, okay, the modulus of B divided by modulus of Z. Okay, that's it. And then we are going to print the current. So the current, okay, the current flowing is, okay, I. Okay, that's the magnitude of your current. So let's print this one. So the current is 0.8696. So 0.87 is good. Okay. So 0.87 is the correct answer if rounded off to the nearest two decimal place. Okay, now let's do this triangle. So in this triangle, we are going to solve for the value of C using the distance formula that we've learned before. Okay, distance formula that we've learned before, no, is okay. Now, what are we going to do here is to solve for the value of C. Now, can you still recall your rectangular form? Okay, of course, that is in rectangular form. Okay, now let's start by calling on your CMAT. So import CMAT, and then let's have this A equals to 61. Let's say A will have an angle of 134 degrees. Okay, A is the magnitude. Okay, A is the magnitude, and 134 here is the angle of A. So let's say angle of A. Take note, now we are not dealing anymore with this figure. We are dealing with complex numbers. So we need to represent this A, let's say A angle of what you call it, 134 degrees, because now we will let this C to A now will be your x-axis, so that we know what will be your y-axis. So let's call this one as angle of A, no, is equals to 134 degrees. Take note, 134 degrees. So we need, since we will be dealing with complex numbers in Python, we need to convert this degree to radian. So CMAT pi, that is 134 times pi divided by 180. That's the angle of A. Now let's have B. So B will have 49 angle of 0. So 49 angle of 0. So angle of B is equal to 0. So why 0? Because we let B now will be your x-axis. Okay, now we need to solve for the value of C. So the value of C, you know, in complex number, this is just A angle of 134 minus B angle of 0 degrees. Now that's how you do it. But we need to take the absolute value, okay? The absolute value of C. So how do you find the absolute value? You can just use the absolute value or the argument, let's say abs, the absolute value or what's called the modulus, no? Abs of what? So we need to find the absolute value of, take note, we need to convert this to rectangular form. Okay, we need to convert this to rectangular form. So we have CMAT, that rectangular form, that rect of A, take note, A, comma, what will be your angle? A angle of A. Okay, take note, A here is the magnitude, and angle A here is your argument. Okay, minus. So take note, this is now in rectangular form. So minus, take note, minus, we have CMAT, dot rect of your angle B, or of your magnitude B, with an angle of 0. Actually, that is the angle of 0, angle B. Now, to be general, let's call this one your angle B, and not 0. So abs here is the absolute value, that is the magnitude of your C. All right, so then print C. Or let's say print, okay, the value of C is, okay, then write C. Let's try if this will work. Okay, the value of C is C. What is C here? Invalid syntax. So print the value of C is C. Okay, the value of C is, okay, what is the error here? Let's try. Okay, no value. The value of C is print C. Take note, we cannot print directly the complex number inside the print function. So we need to separate it. Okay, the value of C is 101.36. Okay, now can you still recall this one? This problem now came out in your quiz number 1 yesterday. Actually today, now because yesterday, because I will be posting this later on. And you can see this now tomorrow. All right, now let's have this one. Let's say I have a parallel circuit having impedances of Z1. Take note, these are Z1 and Z2 is parallel across 12 volts. We have Z1 24 plus negative J. Okay, this is 24 minus J9. Okay, minus J9. So let me correct this one. Minus J9 and 6 plus J8. All right. Okay, let's go here. Now, and we need to find the total impedance. So the total impedance is very simple. So how do you solve for the total impedance? Let's zoom this out. So Z tot, let's label that as our total impedance. So the total impedance for the parallel circuit is actually 1 over Z tot. Yes, Z tot, or 1 over Z1, okay, plus 1 over Z2. Now, if we will simplify, this will become Z tot is equal to, okay, cross multiply. This is actually Z1. This will become Z1 plus Z2 all over Z1 times Z2. Okay. Or I have another one. I have another method. We can just use Z tot is equal to 1 all over the reciprocal of Z1 and Z2. Let's say Z1 raised to minus 1. Let's make it, it is actually the reciprocal of your Z1. Okay, plus, okay, Z2 raised to negative 1. So meaning the reciprocal of Z2. Now we will be using this instead of this one. Okay, because it is easier for us now to take the reciprocal. Okay, now let's call on CMAT. Okay, and we will label this as Z1 equals to 24 minus 9J. And then Z2, 16 plus 8J. Okay, that is our impedance. And we need to solve for Z tot. That is the total impedance of the circuit. That is just 1 all over the reciprocal of Z1. Okay, Z1, how do you put the reciprocal? Z1, or you can say 1 over Z1, okay, plus, okay, 1 over Z2. That's it. No, that's the reciprocal. That's your Z2. Okay, and take note, we need to find the magnitude only. So magnitude, so we need to take the absolute value. The absolute value. So we need to solve for the absolute value. So we can say absolute value of the result, okay, is equal to Z2, mag of Z2. Oh, mag Z, mag Z, okay, no, nice name. And then we are going to print the impedance. So the impedance, the total impedance is, okay, next line we have to print mag Z. Okay. Nice name. So the total impedance is equal to 11.46. Okay, that's it for today. I hope now you've learned a lot, now, especially in using complex numbers using Python. Okay, Python complex numbers becomes easy now if you know how to do this in Python. All right. So I hope no you will do your activity right after this. No, I will be uploading your activity no, after you finish no, watching the video. Okay, that's it. And have a good day.